Morning, Nikias, Shweta, Kritika.
Good morning, ma'am.
Good morning. Okay, now let's start the class. Can you hear me properly?
Yes, ma'am.
Yes, ma'am. Audible, ma'am.
Where is Sharath Kumar today?
Ma'am, his mobile switched off, ma'am, for the past 2 days.
Class? He is not attending any other class or only my class?
Ma'am, all the classes, ma'am.
All the classes. Okay. Now, okay, now let's start. Okay, can you see the screen?
Yes, ma'am.
Yes. Okay. So last class, what we were discussing about the load, what are the loads to be considered for the analysis of all structure. Can anybody summarize which are the loads that we have discussed? What are the loads to be considered for the analysis? One of you. If I say one of you, nobody will answer. Okay, Jagan, tell.
Wind load and earthquake load.
Wind load either.
Earthquake load.
Okay, earthquake load, wind load. Other than that,
Service.
which are the other loads?
Service load, ma'am.
Which service load?
Live load and dead load.
Live load, dead load. And else, wind load and earthquake load. Anything else? Nothing else? Dead load, live load, earthquake load, wind load, impact load. Very good. Impact load. Then anything else? Construction load. Construction load.
Construction load.
Construction load. Construction load is nothing but the load that is during the construction stage. The newly that is the poured concrete weight. Okay. So all such loads also have to be considered, because even if it is difficulty, sometimes it creates an overload and the structure may collapse during construction. So most of us so the other one, the construction load and impact load have they have to be considered because these two okay. So I have even for me there is some network issues are there. So if there is any difficulty in between, please tell me. Okay. So today what I asked you to refer the IS 1893 and asked you to download the IS 1893. I don't know how many of you have done it. Today I will just discuss about.
Downloaded, ma'am. Download, ma'am. I'll send it in the group.
Downloaded.
Yes, ma'am.
Okay. So those who have downloaded, please send it in the group. Which one, 2016 or 2002?
Ma'am, 2016, ma'am.
IS.
Ma'am, if you want, I can share the files, ma'am.
No, I have 2002 with me now. I will share it now.
Okay.
Did you download 2016 or which code? IS 1893.
2016, ma'am. Let me check it again, ma'am.
Okay. Okay. Anyway, 2016. I have only now at present with me 2002, but there is a slight difference between 2016 and 2002, but the procedure all remains same. Okay. So Jagan will put the 2000. See that. Okay, you have to refer that. Today I will just share it and I'll go through that IS code quickly. Okay. Can you see the screen now with the code?
Yes, ma'am.
Yes, okay. So this is your IS 18 revised into 2000.
Ma'am, IS 875 part 3 is 2015, ma'am.
875.
1893 is part 1 is 2016.
1893. 16. 16. So you have to refer that only. Okay. Yes, next class I will refer that because Jagan will forward that.
Uploaded, ma'am. Uploaded, ma'am. You can view that also, ma'am.
Okay, good. So IS 1893 is giving criteria for earthquake resistant criteria for earthquake resistant design of structures. So all the earthquake loads calculations are taken from this particular code. Okay. So here everybody should go through code and understand, because here part 1 is the general provision, part 2 is the liquid retaining wall, part 3 bridges and retaining walls, part 4 is industrial, dams, and so we will be dealing with the part 1, the general provisions and buildings. Okay, so here you have to refer. I will just see India map. So here we can see there are 5 stars, 2, 3, 4, and the entire India is divided into 4 zones. It is into 4 zones. Zone 2, 3, 4, and 5. So zone 2 is the and zone 5 is the highest earthquake prone areas. Okay, so we can see here the north and northeast part of India is highly, that is this zone And here again, you can see this, the northern part is zone 4 again. Okay, so zone 4 again. Chennai, we can see it is in zone 3. All this yellow are blue and zone 2. So very few places are highly seismic regions. Zone 4 and zone 5. Even zone 3 is also highly. It's zone 2 is a low earthquake regions. So the entire India is divided into 4 zones. Okay. Now, terminologies are given here. Some terminologies of earthquake engineering. All these things you have to read, because now at present your syllabus is concerned. We are more particular about the load and how to calculate earthquake. So we need to read all these terminologies that is used. What is importance factor? What is intensity of earthquake? What is liquefaction? All these terminologies, please go through that. There is a magnitude of earthquake. How the magnitude of earthquake is, it is a measure of energy that is, and it is defined as the logarithm to the base 10 of the maximum trace amplitude expressed in microns. The energy that is released. As I was explaining you in the initial classes, when an earthquake happens, the strain energy that is stored in the material, rock under in the molten region under the entire your tectonic plates, it is moving. So during that motion, so whatever energy that is stored, the energy will be released. The strain energy that is stored in the material, the earth material, will be released. So that release is the it's coming at a release of an that is the energy. That energy will travel in the form of waves. That energy will travel in the form of seismic waves. So primary waves, secondary waves, Rayleigh waves, Love waves, so different forms of waves. So this energy which is passing in the form of waves, so through the soil medium, and it travels all from the focus region, from the origin of the earthquake, from the focus to the epicenter. Exactly above the focus on the earth surface, the particular point, the origin of the earthquake is called epicenter. Okay. So it is given here. What is epicenter? Vertically above the focus of the earthquake is called epicenter. Okay, focus will be under the earth where it is originated, but exactly above that on the earth surface, that point from there it starts originating. So the wave. So when the waves hit the object in between, suppose if the building is there on the way of the seismic, will come and touch the building. So the building will start shaking it. Okay. So because the waves will be traveling with a very high speed. So that is how the earthquake we feel it. Okay. Now there is a dam or any other structure or any other object that is we are in the standing on the earth surface, the structures will be affected with the seismic waves. So we measure it using a seismometer. There is a measurement device that is called seismometer. It is called a short period torsion seismometer. Seismic waves, velocity, and the time it is reaching. So that with that values we can calculate the magnitude of the earthquake. So the magnitude usually be represented in terms of between intensity between 1 to 10. We say it is 3, 3.3, 4.5, 6.8, 7.9, 9.8. So as it increases, the intensity or the magnitude of the earthquake increase. Okay. So that is what the magnitude of the earthquake. We have in there are different magnitude measurement systems are there. What we are following in the Indian standard is the Richter's magnitude. So now it goes there. Then finally, I'm not going to explain everything. Okay, this is not, that is beyond the scope of our syllabus. We have a seismic mass. How many of you have learned? Anybody else have learned this? Any? I should know how much I can explain it. Other than Kavya Resu, anybody else learned this earthquake resistant design? Can you hear me?
Ma'am, can you show the slide once again?
Please give response. Which one?
This slide.
This one. Code. And are you not able to see the code?
Yes, ma'am.
I'm asking about this code provisions. How many of you have learned in your UG class? Is that they learn?
Ma'am, I don't remember, ma'am. Maybe it would have come in a structural dynamics in 7th sem, ma'am. I don't remember, ma'am.
That must have. So you others also, Shweta and Kritik?
Ma'am, no, ma'am.
No. Okay. Mikias. Think. Okay. So structural dynamics. There was one unit like the initial engineering seismology. Isn't it? So you please go through this. We'll derive the earthquake load. How to calculate the earthquake load. So here there are some technologies available. How the general principle, how the earthquakes are happening. What I was explaining you just now. Now here, this is what I am interested here in our design of tall structures. How do you consider the load? This I have explained load factors for plastic design of steel structures, and if it is for an RC or a pre-stressed structure, how the load has to be taken. Okay, I hope this I have. In the last 1.5, all these are the partial safety. These are the partial safety factors for the dead load and live load. If there is an earthquake load also coming, the partial safety factor is less because I told you both will not simultaneously. So the partial safety factor can be less. Okay. Now there is one more here. If lateral load resisting elements are not oriented along the orthogonal directions, that means if there is a shear wall or if there is any columns or any other solid vertical elements are there in all the directions to resist the earthquake, then the earthquake, I told you, the earthquake, we can predict that the earthquake will come only in the X direction, the waves will come only in the Y direction, or sometimes it can be in the, depending upon the waves. There are different types of waves. So some will travel, some will travel in a longitudinal direction, some waves will travel in a, so the structure will be affected. We cannot predict exactly in which direction earthquake forces will be. So we need to take all the directions. Suppose X direction, Y direction, Z direction. So depending upon that, the earthquake load also have to be taken, as I was explaining last class. The predominant direction, we can take 100% force in the X direction plus 30% in the Y direction. Okay. And here everywhere you can see a plus or minus. Can you tell me why the loads are taken plus or minus? Usually we take the combination when we take dead load plus live load, isn't it? If it is a gravity, we will never say dead load minus live load. The total load is load. When there is an earthquake load everywhere, you can see it. If you see the top here also, see. You see the first case, 1.5 dead load plus imposed. See, second case also 1.2 dead load plus imposed load plus or minus earthquake load. Why? When the earthquake load comes, there's a minus sign.
Because
Can you tell me?
earthquake, everyone will evacuate the building.
It is not because of that. Everybody will evacuate the. That is where. Okay, so imposed load. So you don't have to design the building for a higher load when there is a chance of earthquake. My question is, plus or when it comes, why there is a minus sign? Plus, why when the total load is taking plus earthquake load alone is not taking? That means the earthquake load is.
Ma'am, it is acting in other direction, ma'am.
Acting
in the opposite direction of the other load.
Earthquake load is correct partly. Actually, earthquake load when we say it is a this direction as well as in the opposite direction, because it is just cyclic loading, isn't it? When it's a wave. Okay, so when you see that when sometimes when earthquake comes, the buildings will be suppose if you take wind load also, when a wind is blowing, what will you see? The direction, the same time next it will be moving in the other direction, isn't it? So a positive sign and a negative sign. It will just explain you one minute. Here. Here. So if you take this building here, can you see the screen now? Slide.
Yes, ma'am.
So this the earthquake load, suppose if it is coming here, the building it can have move in this direction. At the same time, the load can be in the opposite direction also. Okay, opposite direction. So if it, so you know that if a structure is there, this is a structure, then your dead load is also acting in the downward direction. Your line also. So this is my gravity direction. This is my positive direction. This is my positive direction. So this is the dead load plus live load. You cannot say live load is always in a live load. It's a gravity load, downward direction. So the always your dead load will be, live load will be added along with the dead load, because this is my direction. The line cannot change. The dead load is also always gravity towards downward, live load is in the downward direction. So it is always dead load plus live load. But when there is an earthquake, I cannot say it's a load. So the earthquake can come either in this direction or it can be in the other. So depending upon that, so the building will have a sway in this way or this way. So it will go first in then it may move on to this direction, it may come back here. So it is like a cyclic. The load pattern will be like this. Okay. Here it is coming, it can be in the plus direction or it can be in the minus direction. Is it clear? Is it understood?
Yes, ma'am.
Hello? Please give immediate response so that what Mikias is telling different code called, what is EBCS? Can you explain? Can you expand it, Mickey? Okay, so in Ethiopia, maybe I don't know the expansion of that. So depending upon the country, that's what I told. This is what is, because there's another in Japan. If you go, we cannot follow this Indian standard because there is a frequent daily they can see an earthquake there. Okay, Japan people are always so their codal provisions are entirely different from that of India. Okay. So you people should refer all other countries' code, other countries. Codes you have to refer because we are in India. We are learning about the Indian standard, because this standard you can use it only when the Ethiopian building codes. Very good code. So every even in India we have a national building code, NBC. Okay, so for NBC, based on NBC only we do all the construction. All your size, carpet area, entire building standard is given by national. Okay. So similarly, every country will have a different code. You have to refer whenever you get all these things. That is how you have to improve your knowledge. Okay. So what we are discussing here. So there are different load combinations are available. Okay. So depending upon this, we can have again, there are number of load combinations can be X direction, Y direction, 100% in X direction, Y direction, 100% in Y direction. So there are a lot, almost 25 load combinations are possible with the dead load and live load in the earthquake, if we consider the earthquake load. Okay. The X direction, Y direction, Z direction, 100% load in one direction, 30% load in another direction. So all the combinations, if you take, we can almost derive almost 25 combinations are all these load combinations. You have to do it for the analysis. Okay, out of that, which becomes your give you the maximum load that has to be considered. So here you can see here, if there is X direction, Y direction, Z directions, 100% in the X direction plus or minus, then load in the Y direction plus or minus 30% load the Z direction. That I will change it 100% in Y direction, 30% and in the X and Z direction. Then again 100% in the 30% along with the X Y direction. So all these combinations are possible with along with the dead load and live load. Where X and Y are the two orthogonal directions and Z is the vertical direction. Sometimes the vertical direction is very usually lateral load. Okay, either in the X direction or in the Y direction. Z directions are very minimum. Okay. So instead of taking all these things into consideration, there's an alternative method. Earthquake load also can be calculated as square root of, okay, we call it as S versus sum of squares, square root of sum of squares. Okay, so this is an alternate way we can calculate the earthquake load, that is square root of X direction square plus Z direction square. Okay, so as an alternative to the procedure, whatever we are discussing previous, the response earthquake load due to the combined effect of the three components can be success. Okay, so there are different ways you can calculate the earthquake load. Okay, that is one, that is more important. If the building is in a earthquake region, and that too if it high-rise structure, then we move on to that. Then the other important one we are okay. For the purpose of determining the seismic forces, the country is classified into 4 seismic zones. I told you, zone 2, 3, and 4 and 5. Then the distance for a structure shall be determined by the following expression. So this is more important. Everybody should learn. You must have used it. You must have used it. Those who have not used, this is called horizontal. AH represent horizontal acceleration seismic coefficient. So because the load is a lateral load, this is a force. So there should be a seismic coefficient to calculate the earthquake. That seismic coefficient depends upon 4. One is called Z. Z is known as the zone factor. Okay. Z is known as the zone factor that is given the I represents the importance factor. Importance factor depends upon the importance of the building, whether it's a residential building or a hospital building or a community hall or a nuclear power. So depending upon, because you know exactly if the residential building and a nuclear power plant, if you consider 100% nuclear power plant, if there is any damage there, there will be radiation, or if a thermal power plant or any other such power plants, the gases will leak. There will be a lot of this lives. So I represents the importance factor. Then here you can see one R. Capital R represents, so you can see I is the inflation characterized by the hazardous consequences of its post-earthquake functional needs, historical value, or economical importance. That is I. This R represents response reduction. Of these things I'll explain you a little later. Response reduction factor depends upon the type of the structure. Depends upon type, whether it is a normal moment resisting frame, or if it is a masonry structure, or if it is a timber structure, or it is completely special shear wall structures. Depending upon the structural system, the R value will be calculated. Then there is another term called SA by G. You can see SA by G is one term by 2R. Okay. SA by G represents the average response acceleration coefficient that depends upon the soil. Okay. SA by G represents upon type of soil and the time period. Okay. Time period means every structure will have, because if I consider what you are saying, so that particular structure will have a mass, isn't it? And that particular structure will have a stiffness. Stiffness in the sense the call all stiffness based upon the moment of inertia, based upon the dimension, based upon the height. So every member will have a stiffness, and every mass. So based upon the stiffness and mass, there will be a frequency, and there will be a time period for that particular. Okay. I hope you are able to understand, because you must have learned. Are you able to follow me?
Yes, ma'am.
Other, because the whatever I am talking now, it is entirely a separate subject actually. So in that, from that I am taking only a small. Okay. So this SA by G, the average response acceleration coefficient, depends upon the time period of that building and the type of the soil. Sometimes it can be a rocky soil or a medium soil, hard soil, soft soil. So there are different type of soil available. Okay. Type 1. Hard, soft soils. So depending upon that, the SA by G value can be calculated. So once you know the zone factor, importance factor, response reduction factor, and the acceleration, this particular seismic coefficient AH is Z into I into SA by G by 2R. Okay. So once I'll just you see here zone factor. See if the building is in a zone 2, the zone factor is if it's 3, 0.16. Zone 4 it is 0.24 and zone 5 it is 0.36. It is a low, moderate, severe and severe. Now what about the importance factor? Where is it? Tell me.
You're breaking, ma'am.
My voice is breaking.
Yes, ma'am. The entire video, ma'am.
For everybody? Is it for everybody?
Yes, ma'am.
Huh?
Yes, ma'am.
Okay. So you didn't hear what I now is it okay? Now is it clear?
Yeah, but here for only 5 to 10 seconds, then it starts breaking, ma'am.
Okay. I'm out of station, not so there is some network issues here. Okay. That's why initially I told. Okay, at least can you see the screen?
Yeah, it's visible, ma'am.
Okay. So this okay, the important you can see all structures like hospital, school, monumental structures, emergency building, telephone exchange, radio station, community hall, power stations, all such buildings, the importance factor is taken as 1.5. For all other buildings, it is taken as 1. Okay. Now, next one was the ZI, then what is R? R was the response reduction factor. Okay, I'll show you. Can you see this table 7?
Yes, ma'am.
So here you can see a response reduction factor for the buildings. You can see different building systems available here. One is called ordinary. See, normal framed structure with only beams and columns, nothing, no other elements, special elements. A normal moment resisting frame, the response reduction factor is 3. Now, if it is a special moment resisting frame means, suppose if you have given some other additional elements that is there to resist the load, special features that is added in the moment resisting frame, then the value of R is increased to 5. Okay. Similarly, you have steel concentric braces. If you provide, then it is 4, etc., etc. If it is a shear wall, it is 5. If it is building frames that is given here, and different R values are given here. Okay. Now I'll tell you what is the importance of this. I'll just explain you once again. What was the equation? Can you tell me? AH is equal to Z into I into, sorry. One second. Z into I into S, one term SA by G divided by 2R. Okay. So this is called AH. This is the acceleration. The earthquake load is actually calculated. The earthquake load is calculated as AH into this. We have to calculate the seismic load. Seismic load. Okay. This where W is called the. This is called the total weight of. This is weight of the building, considering all the masses, all the structural elements mass together, the total weight of the building is W. So what if you multiply with the value of W, you will be getting the seismic. Okay. So now tell me Z. If Z is the zone factor, the Z value, it's an importance factor. If the building is very important, your importance factor is 1.5. Okay. Now, R is called as the response reduction factor. Response reduction factor. Now I'll tell you this value of R. Where is the R value in this? In the denominator. Denominator. Okay. So if this R, you have seen from the table, it varies between 3 to 5. This value of R is for a normal residence, normal building, normal framed structure. 5 is for a shear wall structure. Shear wall structure means what? It will resist the earth. If I provide a moment resisting frame, and if I provide a special moment resisting or a shear wall structure, how your AH value will be less or more or less, which will be higher. If I use 3, if I use a normal resisting frame with a 3 as the response will be compared to 5 will be more or less.
More, ma'am.
It is AH is inversely proportional to R. So if my R value is less, then AH will be more, isn't it? If my AH is more, then what about my earthquake load? My AH is more, your higher, isn't it? Earthquake load will be higher. But instead of R, instead of 3, if I am using 5, that means where I can resist my earthquake load correctly, then what about your AH value? AH value will become less, isn't it? Use value. So if AH and W, your earthquake load will be less. Okay. So what will happen there? If the earthquake load is less, you can design the structure for a. If you use a special moment resisting frame. So that is the importance of your R value here. Okay. So the third unit will be learning about the structural systems that we are going to adopt it. So similarly, all these parameters. So accordingly, so the AH value has a very important. Okay. So this is how you calculate the earthquake load. Is it clear now? Why? What is the importance of AH?
Yes, ma'am.
Because where it is in which zone, what is the importance of the building, what is the type of soil, and what is the type of structure. So all these parameters are influencing the calculating the earthquake load. Then about your SA by G. Your SA, you can see here how to calculate the SA by G. So I told you SA by G. It depends upon the type of soil, whether it is a rocky or hard soil, and as well as the time period T. Okay. So time, you can have, there is another formula here. Time period can be calculated. Time period T is equal to, there is a formula, I don't know, in structural dynamics, you must, T is equal to 2 pi by omega. Do you remember this formula? Time T is the natural frequency of the building. Okay. How do you calculate omega? The frequency of the building, omega is equal to square root of K. I hope you remember all these things you have learned in structural dynamics. Omega is equal to square root of K by M, where K is called the stiffness of the element and M is the mass. Stiffness and mass of the building, you can calculate the frequency. Once you know the frequency, the time period T can be calculated. That is one way. And code also gives another empirical formula. T is equal to, I'll show you in the code book, it is there. It is towards the end. 0.1 times 0.1 times n, where n represents the number of stories. N represents the number of stories. What is, we have 10-story building. What will be the value of T? If you have a 10-story building, how can we take the T value? Can you hear me? If the number of stories is 10, what will be the T?
1, ma'am.
1 second, isn't it? Time period is 1 second. If it is a 100-story building,
10.
it is 10 seconds, isn't it? Isn't it? So accordingly, if you know the number of stories, T can be directly calculated. Form, or if you know the stiffness and mass of the building, you can calculate the time period. So once you know the time period, and if you know the soil, your SA by G, if the time period is between 0 to 0.1, then this is the first formula, 1 plus 15T. If the time period in 0.1 to, then it is 2.5. If the time period is between 0.4 to 4, then it is 1 by T. Okay. So this is how you calculate the SA by, and for the soft soil, you can calculate the SA by. Okay. So all the three terms, how you know how to calculate it? Z, it is from the zone factor table. By G, from this empirical relation you can calculate, and R from the response reduction factor table. Table 7 you can. So once you get all these 4 values, your AH value can be calculated. So this is the SA by G. Okay. From the expression also you can calculate, or response spectrum graph also you can calculate. You can see the time period here. This is the SA by G. So for type 1, soft soil, medium soil and hard soil. So this curve is called response spectra for rock and soil sites for 5% damping. So for 5% damping. What does it mean by damping? What is damping? Can you tell me what is damping? What is? Do any idea? Do you have any idea what is damping? Have you heard of this term, damping?
Yes, ma'am. Ma'am, is it settling of the soil or a building, ma'am? From
No. Your earthquake building, actually it is completely related to your structural dynamics course. Okay. When I was telling you, when there is an earthquake, the seismic waves will be traveling, isn't it? So it will, if you take you must have done any tuning fork, you must have given a vibration, a fork. Give a vibration, what will happen? It starts vibrating it, and finally it will come to a, isn't it? The tuning fork experiment or simple harmonic motion, your pendulum experiment. Do you remember?
Yes, ma'am.
You all completed your 12th, isn't it?
Energy produced during oscillation.
Energy produced. Light is not energy produced. When you damping will provide you. Suppose if I say, for example, suppose if you what will I say? For example, if I say if you just roll a ball, okay,
Slingshot.
which one?
Slingshot.
Which shot?
On that elastic band.
Tell me.
Slingshot, ma'am.
Okay. If you put a, or in another way, if I say if I take a ball, you allow to roll on a smooth surface and it is on a hard surface, which will stop the ball when you are rolling it on a smooth surface. It will go on rolling, isn't it? But at the same time, if you roll it on hard surface, somewhere it will stop. That means there is a friction there. There is a friction there. So that friction will act as a damping. Similarly, if I put a vibration, the earthquake structures, when it is vibrating, we cannot the structures. Okay, what will happen? If it starts vibrating for a long time, it will break, isn't it? It will break or it will have some damages. So the vibration, any structural element, either it is a beam, a column or whatever it is, when there is an earthquake coming, because of that earthquake there will be a vibration. So that vibration has to be it has to be, so the energy has to be absorbed. What somebody was telling about energy by some means. So you have to put some devices in the structure. When there is an external vibration coming, it has to be arrested. So that mechanism is called damping. So damping in a 1% damping, a 2% damping, there are all these things you must have learned in your structural dynamics. What are the damping devices. Your last unit you must have learned. Okay, it is vibrating, it has to be brought to rest. It has to be arrested, it has to be stopped immediately. So for that you have so many devices available. So that you can incorporate that devices in building, that called damping. Reducing the vibration, that is called damping. Is it clear?
Yes, ma'am.
Is it okay? Understood? Yes.
Yes, ma'am.
So I think so this is how you calculate the AH value. Once you know the AH value, then you have, this is the formula for, I told you. Once the AH is calculated, see your seismic weight, you can calculate, I told you W, the seismic weight can be calculated. Once you calculate your there's another, you can see T is equal to 0.09 by square root of D. Okay. So there are many ways you can calculate the time period of the building. There are many formulas that is given here. Now the basic, the seismic base shear. What is the total force that is coming at the bottom of the building? VB is equal to AH into W. Okay. This is this shear we can distribute it to, and you can calculate how the earthquake load is calculated at each floor of the building. Okay. So I think this Friday again we have a holiday, isn't it? This Friday is Christmas. So we have holiday. Next Monday. Are you able to hear me? I think my voice is breaking in between.
Ma'am, what about tomorrow, ma'am? Class?
Tomorrow, you don't have a vacation. That's what the management told. That's why today other suppose having a vacation, but the management has cancelled the vacation. There is no vacation. So that means you have holidays only on 25th and 1st.
Okay, ma'am.
So 25th is also Friday, 1st is also Friday. So both the days my classes will not be happening. So during this time, what you have to do, to refer you I-93, you have to go through. Next class we will be doing some problems in that. Okay. So so this Friday we don't have class because it's a holiday. Then Monday again I will not be taking class. Instead I will be taking class on Tuesday. Okay. Monday during my time somebody else class. I will be handling the. Okay. So wish you all a happy Christmas.
Happy Christmas, ma'am.
Happy Christmas, ma'am.
Merry Christmas. Thank you, ma'am.
Okay. Happy Christmas. Enjoy. So we will stop the class today. Okay. We will meet you on next